everybody, my name is Professor Rad, and this is Precalc video 2-7, constructing polynomials. So in this video, we're going to construct two polynomials as examples, and we do have one theorem in this video as well. You thought we were done, but not yet. So sometimes you will want or have certain information about your polynomial, and you'll want to create a polynomial to model a situation with that information. So that's what we're going to be looking at here in these examples. So let's take a look at this first one. It says, construct a polynomial that is degree 5, has a leading coefficient of -4, and has zeros of ±1 and 3. So to do this, what I like to do is I like to start out with those zeros, and that's going to set me up with my factors. Because remember that if a polynomial has a 0 of a particular value, then that means it has a factor of x minus that. So I'm going to start out, because I have a 0 of +1, I'm going to have a factor of x minus 1. Because I have a factor of -1, or sorry, a 0 of -1, I have a factor of x plus 1. And because I have a 0 of 3, I have a factor of x minus 3. So that's my first step, is to figure all these out. Cool. So for my next step, I'm going to take a look at the degree. So this needs to be degree 5. And if I look at what I have right now, I have 3 factors. So it's going to be degree 3. So I'm going to need to introduce some more factors into this somehow. I can't introduce x, so I can't like multiply by x squared to get a total of a degree of 5. Because if I introduce a factor of x or x squared, I'm now adding in a new 0. I'm adding in a 0 of 0, which we weren't told the function had that as a root. So I'm not going to do x squared. But what I can do is I can square or one or more of these, or I could cube one of these. So for example, if I were to square this last factor, x minus 3, now I'm going to be degree 2, 3, 4. So I'm going to have a degree 4, and I want to be degree 5. So I could square one of these 2 factors, or I could change this to be cubed. We have a lot of freedom with this because we weren't really given any other conditions. So for instance, I could have cubed x minus 1 instead. That would be fine. Or I could square this first one and square the second one. And now I'm still degree 1, 2, 3, 4, 5. So I'm still degree 5. So it's up to you based off the information that's here. There's nothing prohibiting me from these options. Sometimes there will be, and we'll see an example where there's some conditions in place where you have a little bit less choice. But for this one, we have all the choice we want. Which of these roots gets doubled? We also are told that we need to have a leading coefficient of -4. So right now, if I look at what's happening, I'm eventually going to have an x squared times an x squared times an x. And all of those have a leading coefficient of 1. So I'm just going to throw a -4 outside. Now, unlike putting just an x on the outside, multiplying by a -4 is not going to change the roots. This is because the -4 isn't a variable. All it's going to do, in this case, it's going to do a vertical stretching and reflecting, right? Going back to our transformations. So this -4 in front is going to ensure that we have our leading coefficient of -4. These 3 factors are going to ensure that we have these as our roots, as our zeros, and the exponents that we've chosen are going to lead us to a polynomial that has degree 5. So we're going to do another example, but before we get there, let's look at a theorem that's going to come into play. So here's theorem 9. It doesn't have a name. That's going to be important when it comes to constructing a polynomial with non-real complex roots. So theorem 9 says, let's let f of x be a polynomial with real coefficients. If r equaling a plus bi, and in this case, it's a non-real complex number. So that means the coefficient of I is not 0. So if a plus bi is a 0 of your function f, then its complex conjugate, a minus bi, is also going to be a 0. And here's why that happens. So if I have a polynomial that has real number coefficients, but it has a complex root, that means that there has to be something in the multiplication process that happens to turn that complex root, it's got to multiply and cancel somehow so that I only get a real value. So when you multiply a complex number with its complex conjugate, let's check and see if we get a real number out of that. So if I take a plus bi and I multiply it by a minus bi, see, I'm going to get a squared minus abi plus abi, and then minus b squared I squared. So we can see that the I terms, the negative abi and the positive abi, are going to cancel each other out. And remember that I is the square root of -1. So if I square I, that's going to give me -1. So that means this minus b squared times -1 turns into a plus b squared. Bring down my a squared here. So if I multiply a complex number by its complex conjugate, I'm going to get a real number out of that because the coefficients are reals. And if I add the sum of real numbers, I'm going to get a real number out of it. So what this means for us is if we are constructing a polynomial with real coefficients that has complex roots, let's say I were to tell you that one of the complex roots is 2 minus 5i, you know the other one is going to be 2 plus 5i. So you have to take that into consideration. So let's do an example where we have to consider that. So let's look at our second example of constructing a polynomial. So this time we want to construct a polynomial with real coefficients and it has a y-intercept of 0, 8, and it's going to have a complex root of 1 minus I and 2 real roots of -1 and 2, as well as a degree of 4. Just a few requirements for us here, right? So as before, I'm going to start out with the roots leading to the factors that I'm going to have. So for this one, we have 2 real roots of -1 and 2. So root of -1 means I'm going to have a factor of x plus 1. And a root of 2 means I'm going to have a factor of x minus 2. Now we also have a complex root, so I'm going to have to subtract that as well. So I have x minus, and in parentheses, 1 minus I, because I want to make sure I don't forget any distributing that may need to happen. So that's from the first part of just stating my roots. I notice 2 things. So thing 1, I'm noticing this complex root, and that's different from real roots. I've got that last theorem stuck in my head. And I've also noticed that there's a degree of 4. So right now there's 1, 2, 3 roots, so, or factors rather. So I am going to need another factor to get up to that degree of 4. And that last theorem that we just looked at is how I'm going to get there. So this time, instead of squaring one of the factors, I notice that I have a complex root, which means by that theorem, I need to have its conjugate as a root as well. So if I have to do 1 minus I also have to do 1 plus I as a factor. So the complex conjugate of 1 minus I is going to be 1 plus I. So now I have my factors that are going to satisfy all those nice conditions. And there's 1, 2, 3, 4 of them. So we're going to be degree 4. So we hit the degree 4 requirement. We've got our roots. We've satisfied the theorem so that we'll get our real coefficients. So that's all good. The one thing we haven't hit yet is this y-intercept of 0, 8. Now, some folks have a tendency with these problems to say, well, if I take the polynomial function and I shift it up 8, then it's going to hit the y-axis at 8, right? No, not necessarily. Like in this case, I don't go through the origin, so I don't know where it's hitting the y-axis. I don't know where this will hit the y-axis right away. So if I just shift it all up by 8, I might not actually be hitting 8, might be hitting something else. Also, when we're constructing this polynomial, these zeros are needed because that's going to give us our x-intercepts. And if we shift the function up, we've now just lifted those x-intercepts up off the axis. So we can't shift shifting is a transformation we don't want to use to try and obtain a particular y-intercept. However, we can stretch, because if you stretch, it doesn't matter that these are crossing, like here I have the point -1, 0. So if I stretch that 0, it stays 0. It's not going to move. So to stretch, we're going to need to multiply by a non-zero coefficient. So I'm just going to call that a. Now we have to solve for it. So when x is 0, y is 8. So this is similar to like when we needed to find a on our parabolas, on our quadratics. So we're going to do the same thing here. We're going to plug 0 in for x, 8 for y, and then we can solve for a. So here's my 8 for y. And then 0 plus 1 is 1. 0 minus 2 is -2. Okay, so now we have 0 minus 1 minus I. I'm just going to throw that in there. And then here as well, 0 minus 1 plus I. Okay, so 1 times -2 is a -2. So I'm going to have 8 is -2a. And now let's simplify these complex factors here. This will give me a -1 plus I. And then this will give me a -1 minus I. Now, we just saw when we had the a plus bi times a minus bi, we saw a plus bi times a minus bi gave us a squared plus b squared. So if you want to remember that as a kind of formula, that can be really helpful, because here we have -1 plus I and -1 minus I. So I can apply this formula and just rewrite it as a squared plus b squared, where the a and the b are the coefficients. So -1 squared is 1, and my coefficient of I is 1. So that's going to be 1. So that actually just gives me 2. So this is going to give me 8 equals 2 times -2, which is -4a. So I can divide both sides by -4, and that's going to give me -2 equals a. So I'm just going to go back up in here and put in -2. That's my solution. So we are building on concepts that we learned from before, right? So our concepts of transformations and some of those techniques we had with our quadratics, we can see are coming into play with our larger polynomials. So that's going to conclude this video of constructing a polynomial. In the next video, we're now going to see some more properties. Now we're going to start to see how can we use polynomial information to help us graph the polynomial. Or if I notice that I have a root that's just got an exponent of 1 versus a root that I'm, say, squaring, does that change the shape of the polynomial? So that's what we're going to be looking at in the next video, concepts of things like multiplicity and power functions. So I look forward to working with you on those concepts in the next one. I hope this video helped you to construct some polynomials, and may you have a wonderful day. Bye for now.